Alright, this video is on simplifying square root and cube roots. For some reason I find this topic a little bit difficult to present. It requires a strong understanding and number sense, being able to find factors of things and etc. And I think that's part of the problem. But basically what we're going to do is we're going to look for ways to simplify radicals. What that means is underneath the radical, if it's a square root, you can't have any perfect squares. If it's a cube root, you can't have any perfect cubes that are factors of that number. There kind of are two ways that we can do this. One, we could do it by using numbers that we know are perfect squares or perfect cubes. Or 2B, we can use a factor tree method. Now, the perfect square and perfect cube way is nice if the numbers are small and we know we can see the factors of them. However, we also can talk about simplifying fourth roots or fifth roots, in which case this first method kind of falls apart. So we kind of all need the second method in our pocket. So as a result, a lot of people kind of default to this method. I'll go through a couple of examples using each of the methods so you can kind of pick and choose. Both methods will always give you the same results. So you're going to have to pick the one that, one, you're most comfortable with, and two, that works in any given situation. So even for myself, who's been doing this for a lot of years and teaches it, sometimes I'll use method A and sometimes I'll use method B. It just depends on if it jumps out at me that there's a perfect square that's a factor of the number or a perfect cube that's a factor of the number or not. If it doesn't jump out at me, then I go to the factor tree method. Just be careful along the way, and we'll talk about that as we go. All right, so let's talk about method A, and then we'll talk about method B, and then we'll do a couple examples together. So method A, using perfect squares and perfect cubes. First of all, a perfect square and a perfect cube, it's the resultant number when you raise a number to the second power for perfect squares. And for perfect cubes, it's raising a number to the third power, so just out of order here. These numbers right here in this column, they're all numbers squared. Those are my perfect squares. They're helpful because if I take the square root of a perfect square, it gives me the number that was squared initially. So the square root of 4 is 2 because 2 squared was 4. The square root of 9 is 3 because 3 squared was 9, etc. Okay, so that's how it's going to be useful to us. I can do the same thing with cubes. 1 cubed is 1, so the cube root of 1 is 1. 2 cubed is 8. So the cube root of 8 is 2. 3 cubed is 27, etc. This one would equal 4. It's 4 cubed. This one's 5 because 125 is 5 cubed, etc. all the way through. Okay, so I hope that makes sense, at least where these numbers are coming from. And I'll leave this here as a reference for you as we're moving forward. The property of radicals that we're using to help us do this is actually the fact that the nth root, so n is just called the index, some number, the nth root of x to the n is always n. So when the exponent and the index are equal, they undo each other, they're inverses, they cancel each other out. Okay, so the square root of 25 is 5. You all know that. The reason is because square root has an implied 2 here, and 25 is 5 squared. So the index and the exponent are equal, so this comes out as just one group of 5s. The third root of 2 cubed, that's the same thing as me saying the third root of 8. That equals 2 because the index and the exponent are equal, so they undo each other, give me with just the base of that exponential part. To simplify with perfect squares and cubes, your job is to find the largest perfect square or the largest perfect cube that is a factor of the number underneath the radical. It's called the radicand, it's a fancy word. And then you're going to simplify that perfect root, so change it into its integer value, and then leave the other part underneath the radical. Sounds terrible, but it's actually not so bad. Again, we already looked at that slide, so these are the numbers we're looking for perfect squares. These numbers here, 1, 8, 27, 64, 125, 216, 343, I never remember these ones, so those 7 are the numbers that we're looking for perfect cubes. Second method is the factor tree method. So when you simplify with the factor tree method, you need to pay attention to the index, that n, that number right there, because it's telling you the group size that you need in order to take out one group from the radical. It has to be a positive number. It's going to be an integer. To simplify the factor tree method, you're going to factor the number, the numeric part, into the product of its prime factors. It's called the prime factorization. So prime numbers are 2, 3, 5, 7, etc. Dot, 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 dot. Okay? When any number is a factor n times or a multiple of n times, then one group of that number comes out, not out of the radical. Any number of factors over that remains under the radical. Any numbers that come out of the radical get multiplied together. Any numbers that remain underneath the radical also get multiplied back together. We can also do this for variables, and we'll do that in an example as well. Okay, so there's our two methods. Let's see them in action, because that's going to make this make more sense. All right, so square root of 720. So again, there's an implied 2 here, square roots. We don't write the 2 when it's square, but I'm just going to put it there for now to remind myself that. So in the square and root method, I want to take 720, and I want to think of the largest perfect square that divides into that. Now for me, the number that jumps out is 36, because 36 times 20 would give me 72. Or 36 times 2 is 72, so add the 0 and I get 720. But is there a larger one? I think the answer is yes, but off the top of my head, I'm not sure what it is. So I'm going to go with 36. I don't have a calculator in front of me, so if you have a calculator in front of you, at this point, I would go through and I would divide 720 by larger numbers to see if any of these guys after 36 are factors of 720. And I think that maybe this one right here is, but I don't know that for sure, so I'm going to just go with what makes sense to me. So I have 36 and 20. I look at 20, and there's actually a perfect square that divides into 20, and that's how I know there was a bigger number. So 20 is actually 4 times 5, right? That I know. So this is perfect squares times the non-perfect square. Now I'm going to evaluate my perfect squares. The square root of 36 I know is 6. The square root of 4 I know is 2. This guy is not a perfect square, doesn't have any perfect square factors, so it stays under the radical. Numbers out in front get multiplied together, so my final answer here is 12 times the square root of 5. So, like I said, 144, 12 squared was the factor of this. Didn't come to me, so I went the smaller one and took out 2 perfect squares, and that's okay. This is actually a good point to make because it's possible that right here I say this is 6 times the square root of 20. That's true, but it's still not simplified because there's still a perfect square factor of 20. So when you're simplifying, always check at the end to make sure there's no perfect square factors of your radicand if you're using the square root or cube root method. The factor tree method, that's not going to be a problem. So let's try it with method B, the factor tree method. Factor tree method says take your number and think about all the numbers that are factors. So first, let's just start with a pair of numbers that are factors of 720. Now, for me, what jumps out, because it ends in a 0, is 10 and 72. Any pair of numbers that multiplies to 720 that jumps out is a place to start. At the end, our answers will all be the same. Now, I'm going to keep factoring these numbers until the results are all prime. So this is 2 times 5. 2 is prime and 5 is prime. I'm circling them so I don't lose them in my factor tree. 72 is even, so I know it's divisible by 2. And 2 times 36 is 72. 36 is not prime, so I keep going. 36 is 6 times 6 is what jumps to mind, so I'm just going to go with that. 6 is 2 and 3, and again, maybe different numbers are jumping to mind for you, but at the end, our list of numbers should be the same. So I only want the prime numbers at the bottom. So this is 1, 2, 3, 4 2s, so this is 2 times 2 times 2 times 2. So that's all those 1, 2, 3, 4. And then I have 2 3s times 3 times 3, and then I have 1 5. So this here is the prime factorization of 720. Just I mentioned that in the notes, so I just want to point out what I was talking about when I said that. Okay? All right, so now, factor tree method says the index here Let's see if I have, okay. The index is the group size. So the index was 2. So I want to think about groups of 2. So I have one group of 2 2s, one group of 2 2s, one group of 2 3s. He does not meet the group size. He is stuck in the radical party. So let's come back to this. So I said that if they meet the group size, they get to come out of the radical. So a 2 is going to come out of the radical. Sorry, this is all underneath the radical here. Another 2 is going to come out of the radical. A 3 is going to come out of the radical. No partner, stuck inside the party. See you later, 5. You're stuck inside. All the numbers out in front get multiplied together. 2 times 2 is 4. 4 times 3 is 12. And any numbers underneath get multiplied back together. No numbers underneath besides the 1, so I just get square root of 5. So final result, 12 square root of 5. You'll see you get the same answer either way. Let's try another one. I changed the group size. Dun, da, da, da. So now it's a cube root. Cube root of 108. Now I'm much better with perfect squares than I am with perfect cubes. So before we do the cube root method, I'm going to take a quick peek. 1080 is my number. I think, let's see, I think that 27 times 4 is 108. So that means that 27 times 40 is 1080. There's an 8 in here though. 2, 3, 6. So now I'm thinking like of this guy here. I think that 216 times 8, and you will be doing this with your calculator. I don't have a calculator in front of me, so I'm just kind of doing it. No, that doesn't work. I'm just trying to do it in my head. That's not a good plan. Let's see here. 216 times 5. That's times. 0, carry the 3, 8, 10. There it is. So 216 times 5 is where I'm going on this one. Again, if I had a calculator, that would have been a lot easier. So I'm saying the third root of 1080 is the cube root of 216 times the cube root of 5. Cube root is 216, we just saw, was 6. 5 is not a perfect cube, it stays put. So that work is short, but the work that I had to do to get up to there, this business, kind of annoying. I'm just saying. So if I were actually doing this question, I would use the factor tree method because this isn't intuitive to me. It doesn't come to mind immediately. So I'm going to say, let's do the factor tree method because it always works. The only thing that's changing is the group size. So I'm going to try to break this down. It's divisible by 10 because it ends in a 0. So I'm going to say this is 10 times 108. That's where I went to. Maybe you did something else. That's fine. 10 is 2 times 5. Those are both prime. Let's see. This is even, so it's divisible by 2. 2 and 54, which is certainly not prime. That's even, so it's divisible by 2. 2 and 27, that's not even, but it's divisible by 3. It's 3 and 9. 9 is 3 times 3. So there's my big fat list. So this is equivalent to the third root of 1, 2, 3 2's, 2 times 2 times 2, and 1, 2, 3 3's, 1, 2, 3, and this 1 5 at the end. There's that. Let's see, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7. So make sure I didn't forget anything because I need all those in order to get my final answer. So again, our group size is 3. So I need a group of 3 in order to leave the radical once. There's that. So let's go back to our pen. So one group of 2's comes out. One group of 3's comes out, and that poor 5 gets stuck underneath the cube root by himself. So this is 6 times the cube root of 5. Again, final answer. Make sure you have that little 3 as your index, otherwise your answer is wrong. And there's that. I think one more question. Ah, yes, one with variables. Let's see, how does that impact it? Also, this weird 5 out in front. What is that about? I don't know. So let's see what we can do here. All right, cubed root method. It's cubed root because there's that 3. Let's see here. So I want to try to break this into a cubed root times a non-cubed root. Same thing for each of these. So let's see. The 5 stays put. Let me rewrite this first. The 5 is a coefficient. It's just going to get multiplied together at the end. So I'm just going to carry it along in each of my steps. So this is 27 is a factor of 54. So this is the cube root of 27 times the cube root of 2. X to the 4th is the cube root of x to the 3rd times the cube root of x to the 1st. And y to the 6th is the cube root of y to the 3rd cube root of y to the 3rd. That's everything broken up into perfect cubes. All right, so ones that are not perfect cubes are here, and everything else is. So I get 5 times this guy gives me a 3. This guy gives me an x. This guy gives me a y. This guy gives me a y. And then I have third root of this 2 and this x. Things out in front, multiply back together. This gives me 15xy squared cube root of 2x. That's cube root method. Factor tree method. Here we go. 5 third root 54 x to the 4th y to the 6th. I'm going to deal with the number part first and then kind of the x's and y's at the end. Again, remembering this 5 has to be, I'm just going to bring it down here. This 5 has to be part of my answer at the end, and I'm going to have to multiply it by whatever I get from simplifying the radical. 54, 2 and 27. 27, 3 and 9, 9, 3 and 3. So this is 5 cube root of 2 times 3 times 3 times 3. X to the 4th is just x, 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 x. I'm leaving myself enough space here, so let me erase this parentheses. There we go, come back. Okay, y to the 6 is y, 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 y. There we go. Now I can think about my groups. I want index of 3, right? So group size 3. There's one group of 3's, one group of x's, 1, 2 groups of y's. So let's now simplify that out. The 5 from here comes down. Groups of 3 come out. So 3 3's, 3 x's, 3 y's, 3 y's. Remaining inside 2 and x. Multiply these together, 15xy squared, third root of 2x. That felt much better to me just because it's a process that I can always do, whereas this, oh, that felt really annoying to me. So I probably would have chosen the factor tree method there. So there's an example of each type. You choose which works best for you. Just make sure that you are careful in either way.